Hello everyone, my name is Scott Keating and I'm a product specialist here at Side Effects Software. And today I'm going to walk you through the creation of a waterfall simulation using Houdini 12's Flip Fluid Solver. Let me just bring up an animation here as an example. So this is a waterfall that was simulated and rendered using Houdini 12, and it's the type of effect we're going to try to achieve today. So if you look closely at what's happening here, you'll really see two types of motion. There's this underlying waterfall simulation, which is really the clear sort of water you see here. And then there's this white water splashing foam action. And those two types of motions are really going to break down into two separate simulations. There'll be an underlying waterfall sim, and then the results from that simulation will drive the whitewater simulation. So let's just jump over to Houdini and get started. So the first thing we're going to need is a landscape for the fluid to interact with. Something interesting as a collision object. In general, when working with fluid simulations, it's always a good idea to have something underlying the fluid sim that will help create splashes and turbulent motion, because it's this type of action that'll really bring the animation to life. So let's just start with a grid. Dive inside and put down a mountain sop. Connect these guys up. So we probably don't have enough detail right away to begin with, so I'm actually going to go back to my grid sop and just pump up the rows and columns. I'm also going to bring it in a little bit so you've got more of a rectangular shape. Yeah. So going back to the mountain sop, I think we've started out with a little too much roughness, so let's bring down the height a little bit. We don't want to go too low because we definitely want to keep some of this roughness in the grid, because it definitely will help the fluid simulation later on down the road. Maybe something like that. Let's turn off the construction plane as well. So from here I'm just going to do a series of extrusions to give the landscape a stepped appearance. I'm going to put down a poly extrude node. Now in general you can use this handle, but I'm actually going to use the global parameters in order to extrude straight up along the y-axis. And then from here I'm just going to reduce my polygon selection a couple of times and hit Q, and then once again just use the global parameters to extrude straight up along the y-axis. Now this is a fairly simple landscape, obviously. You can take the time to do something more detailed or realistic, but this will do for our demonstration purposes. And maybe the final level will be quite a bit taller than the others, so that the water has to fall some distance at first. Yeah, that will do. And feel free to go back and adjust the mountain sop to something that looks good and rough or interesting. I think that's probably rough enough, but let's just adjust the offset here until we find a nice... There we go. That's got some nice dips and bulges in it. So once we have this basic model, I'm going to do a couple of things to clean it up a bit before we send it off to our simulation. I'm just going to select an edge and hit L to select the whole loop. Then I'm just going to put down an edit sop and reduce the scale on the y-axis to 0. This just flattens out the bottom of the model, and it'll help us have something nice and clean to work with. While I still have those edges selected, I'm also going to put down a poly cap node. And if you go on the bottom, you'll see we've just basically put a giant polygon along the bottom of the model. And this will help DOPS create a nice collision geometry for our fluid. So I'm going to jump up to object level, just zoom out a little bit. Then I'm going to go up to this rigid bodies tab here at the top of the screen. And I'm going to select the static object shelf tool. When you do that, it'll ask you which object to turn into a static object. So let's select our grid and hit enter. Now that's created an AutoDOP network for us. It's also done a couple of things inside our object itself. But for now, let's just dive inside the AutoDOP network and take a look. So basically, it's taken our grid object and it's connected to a static solver and added some gravity. And we do want to make a couple of adjustments here right away, just that will help give us more accurate results when the fluid sim comes into play. So if I click on the grid object and scroll down a little bit, you'll see we have this physical and this collisions tab. We want to go to the collisions tab and scroll right to the bottom. Here we have a show collision guide geometry. So let's turn that on and take a look. Now this red object you see sort of inside here represents the collision volume. And you can see that it's not quite picking up all the detail of our actual landscape. So the way we can adjust that is just going up to this uniform divisions and increasing the value. Let's try something like 100. There you go. You can see that we're picking up just about all the details. Now you can obviously increase this number quite a bit higher if you really need to capture every single sort of nook and cranny in the landscape. But for now, this will do. So let's make sure we turn off the show collision guide geometry and jump up to object level again. And just to keep things clean, I'm just going to rename this grid object landscape. And then inside here, I'm going to do the same thing. This will just help keep things clear once we have a slightly more complicated simulation happening. So the next step is to create a emitter for our fluid sim. So let's get started on that. To create an emitter object, all we really need is a piece of geometry. So I'm going to put down another grid. I'm just going to dive inside. And I'm going to adjust the size a little bit, since we definitely don't need something quite that large. Shrink it down. Just use the handles to adjust it. And then obviously put it at the top of our waterfall, since that's where we want the water to come from. It's a good idea to put it fairly close to the top, but you definitely want to make sure it does not penetrate our landscape geometry. And once you're happy with the placement, that looks pretty good, just jump up to object level again. Before we do anything else, let's just rename this into emitter geo. So select your emitter geo node, and then go up to the particle fluid shelf, and hit this emit particle fluid shelf tool. It's going to ask you if we have a fluid already, and we don't, so just hit enter. Immediately it does something, so let's just take a look. You definitely have some particles sitting up here at the top of our waterfall. And it's also added a create surface volume node to our emitter geo, and a couple of other nodes. But for the moment, let's just ignore that and actually dive inside the AutoDOP network. Things are a little bit of a mess at first, so if we hit L, that will just clean things up a bit. So basically, it's created this fluid simulation over here. And it's merged it in with our original landscape, which is exactly what we want. This is our emitter here, and you can see it even says source from emitter geo. There's a couple of options on here you can adjust, but for the moment, let's just zoom out and hit play to see what kind of result we get. Well, it definitely is creating a fluid sim, and you can see that it is colliding properly with our landscape, but obviously a lot of the fluid is falling off the side, and sort of we don't really need that to happen. So if we zoom out, you'll see this purple container which surrounds our landscape. And that's actually the limit of our fluid sim. If we click on the Flip Fluid Solver node, it will give us a couple of handles, and we can use those to readjust our fluid limits. So if we jump back to frame 1 and just use the handles to scale this in, so it actually fits nice and snug over our landscape. In fact, it's probably a good idea if you actually have it come in just a little bit past the edges. That way we can be sure we've contained all the fluid. Let's scale this down here. Go into wireframe mode just to be sure that it's where we need it to be. Scale down the Y. You don't have to be perfectly precise with this because you can always readjust it later. But it's definitely a good idea to get this, exactly into position because it will help optimize your simulation. So if we hit play again now, you'll see that we don't get the fluid streaming down off the sides of our waterfalls. But at the same time, we're not getting quite as much water flowing down over the surface as we might expect. And that's because the particles at the sides of these containers are actually just getting deleted. And that's not what we're looking for. We want to make sure that the fluid is just contained inside of here. And there are some very simple options we can use to make that happen. Before I do that, I'm going to go to the Flip Fluid object and go to the Guides tab and then the Particles tab. Under Visualization, I'm going to just change this to Particles. This is purely a personal preference. I find it easier to follow what's happening with this visualization, but use whichever one you're comfortable with. Now if we jump back to the Initial Data tab and we go down to the bottom, we'll see this Closed Boundaries checkbox. If we turn that on and then hit play again, you can see that we're getting quite a lot more fluid going down our landscape. And that's great. That's exactly what we want. Unfortunately, when it reaches the bottom, because we've closed these boundaries, it's essentially going to start filling up our fluid container, and that's also not what we want. Luckily, we can actually adjust these boundaries sort of per axis. If you look at our gnomon down here, you can see the positive Z is this side of the container. So if we uncheck that, we can actually get our simulation to behave more the way we would expect. If you just hit play again, our waterfall behaves more or less the way it did before, but when the fluids reach the bottom, rather than collecting and pooling down here, they're just going to start getting deleted. And that's great, because what we've essentially created is an unending waterfall where particles are created at the top and deleted at the bottom. This is very efficient. So you want to adjust this depending on your scene and what kind of landscape geometry you have. It's a great way to optimize what's happening so that you don't needlessly create or store a whole lot of particles. And really, that's all you need for a waterfall style simulation. But we can definitely make it more interesting than this. So let's just back this up, hit play again. So one of the key things that's going on here that's a little uninteresting is that the fluid is more or less smoothly traveling across the surface. Having the turbulent landscape definitely does help the appearance. It's creating little places for the water to get caught and turn and sort of move, and that's great, but we can definitely push it further than that. So let's jump back to frame 1 and go up to object level, and then dive down inside our emitter geo. If I go to the Create Surface Volume node, which is the one the Shelf tool created for us, I'm just going to turn off this ISO surface visualization and then zoom in. You can see that these are the particles that are being used for our fluid source. And if I scroll through it, in fact, let me just turn on Hide Other Objects. And if I scrub through here, you can see that the particles are sort of randomly being created within this volume. But they're not really moving. The overall shape is staying the same. And that's not what we're looking for. We want an emitter that sort of moves and gives a little sort of fluid motion before the particles even are created. So a very simple way to do that is actually to use the Mount node, the same one we used when creating our landscape. If I drop that down, get a little more room here so we can see what's going on. Maybe adjust the height a little bit. You can see we've changed the shape of our initial grid, and if I go to the Create Surface Volume node again, now you can see we've changed the shape of the emitter. And that's great, but it still doesn't really change over time. Although the particles are sort of jumping around inside the volume, they still aren't changing shape, and we definitely want to adjust that. So go back up to the mountain SOP, and in the Offset tab, in the Y parameter, put $FF. $FF is a very simple expression that basically grabs the current frame number. So if I evaluate that, you'll see that it says 1, which matches up to the frame number. And if I scroll through to frame 48, it now reads 48. So that's basically creating a simple animation in the offset. But it's probably too fast right now. It's too chaotic. So let's just divide that number by, say 20. And if I hit play now, and turn on our real-time playback, you can see we actually get a kind of nicely deforming surface that almost looks a little bit like water. So that means we're on the right track. And now if I go down to our Create Surface Volume node and visualize it, you can see that our whole volume is changing shape. So that's going to help us quite a bit when we get down to the simulation again. But let's add a little more interest. On the Create Surface Volume node, you'll see this Velocity Volumes tab. And even though we have this visualized as streamers, we're not actually seeing any velocity visualization here at all. And that's because there is no velocity parameter just yet. Velocity attribute. So let's create one. I'm going to drop down a VOPSOP. Connect to the first input and then dive inside. And we're going to do a very simple network here. We're going to put down a turbulent noise, connect the point position value to the position parameter, and then this noise value to the point velocity attribute. And as soon as I've connected that, we've created a velocity attribute on our grid, which is getting picked up by the fluid source node, and then visualized as these sort of lines. Let's just jump up again and go to the Create Surface Volume node. Make sure we're on the Velocity Volume tab and go down to Visualization. If we change this plane parameter to the ZX plane, now you can see that we've got a velocity sort of pointing up and to the left. But again, it doesn't change over time. It's always pointing up and to the left, and that's not what we want. So very similar to the mountain SOP, turbulent noise has a lot of parameters that actually are exactly the same. So we're going to promote those by clicking on this little gear icon. This may go off the edge of your screen, but it says promote parameter, and that's the one we're looking for. It'll change it to this sort of plug icon here. Let's do that for a couple of these guys. I'm also going to change the signature from 1D noise to 3D noise. And then also from alligator noise to sparse convolution noise. That's just a personal preference. I happen to like the way sparse convolution noise looks. And if you look in the visualization, things have gotten a lot more interesting. So let's jump up to the top, and you'll see that all the promoted parameters appear here on our VOPSOP. So we're going to do exactly the same thing as we did on the mountain SOP. We're going to use a $FF expression and divide it by 18. You can play with whatever values you feel are good in there. If we scrub through the timeline now, you can see that we're changing shape over time, but also the velocity vectors are sort of swirling and pointing in different directions. And that's really going to help give us a more interesting look when the particles are originally created. So if I jump up to object level right now, and then down into our DOP network, I'm going to go to our source surface from emitter geo, which is this source volume node. You can see we have a scale velocity. Just to make things really clear, I'm going to set that to something like 25. And right away our particles have sort of changed color, indicating they have some velocity on them. So if I zoom out here and hit play, right away there's a very clear difference. Our particles sort of splash crazily around the container. But you can tell that immediately we're getting a much more interesting result. So let's just go back to frame 1 and take a look at our waterfall. Let's change the scale velocity to something more reasonable, like 13. And then hit play. Now when the water flows down over the landscape, it's sort of getting pushed and shoved in different directions. So it's creating a much more turbulent look than when the particles simply fell straight onto the landscape and sort of slid along the surface. So really combining those two aspects, creating velocity, changing the initial shape of the particle source, but also having a turbulent, interesting landscape for the fluid to interact with. They all combine together to give us something that feels more like a gushing, turbulent river, rather than a sort of very static, smoothly flowing waterfall. Let's just take a look at this again. So now that we have a system that actually works pretty good, let's take advantage of Houdini's procedural workflow to make a couple of adjustments to this waterfall. I feel like we could maybe raise up this top section a little more and create a more interesting drop here at the top. So let's just jump back to frame 1, go up to object level, jump into our landscape, and if we go to this last poly extrude, which was the one we used to create this top piece, and just scale that up quite a bit more, maybe twice as high. Then go up to object level, select our emitter geo, dive inside, and on the grid, if we just change the center, in fact let's just ghost other objects again, and then just move this up so it sits on top of the waterfall again. Now if we go to object level and back down inside of DOPS, you can see that everything is updated fine, which is the great advantage of Houdini. We can make these changes as we go. We don't have to decide everything up front. So if I hit play now, you can see our simulation begins running again, and we've changed the look of the waterfall completely. Now we have this very large drop with a lot of fluid splashing and gathering in different areas. So our next step is to start gathering the data we're going to need for our whitewater spray foam simulation. So the first thing we're going to want to do is write out this particle fluid simulation so that we don't have to do this simulation every time. So if I just hit escape and go back to frame 1, I'm going to jump up to object level. So if we jump inside this particle fluid node, which was created for us by the emit particle shelf tool that we used originally, we'll find a couple of things. One is this DOP import node, and that's actually just bringing in our particles from the simulation. If we hit play now, you can see that they start coming in. But the one that we're interested in is this import particle node. Let me just make a little room here. If I click on that node and then make some room for the parameters, you'll see that it's importing a couple of things. Right now it's the geometry field is being brought in, and that's really just the particles that we've created in the fluid simulation. But there's a couple other things available to us which will be helpful when we do get to the whitewater simulation. And one of those is this vel field, which is really just the velocity of the fluid simulation. And this will definitely be helpful when we start trying to push the whitewater or spray particles around so that they match up with our previous simulation. So we definitely want to import that one. Also, if we hit this plus icon, we'll get another space to input another field. And we want to put down surface. Now the surface field is one that will become really important because it basically gives us an indication of what is inside the fluid surface and what is outside the fluid surface. And being able to test that boundary will be very helpful when it comes down to our spray simulation. But before we get to that, we're going to need to write out this information. Now technically speaking, you could run one simulation directly into the next one, but it's always nice that once you've sort of locked down a part of your simulation, to write it out to disk, just so you don't have to waste processor time re-simulating something that you've already done. So let's just put down a ROP output driver and plug it into the import particle node. Change render any frame to render frame range, and 1 to 240 is probably fine. Now for this output file, you're going to want to pick somewhere that makes sense. So let's just put down a original particles folder, and then call this base waterfall underscore $F. And the $F, like we saw before, is basically an expression that will write out a new file for every frame and make sure that it has a properly named file name to go along with it. You can also turn on this save in background, although if you are just waiting for this to write out, it's not absolutely necessary. Well, that's set up. Just hit the render button. Now while that's cooking out our simulation, I do want to mention that at very high resolutions these particle sims can take up quite a large amount of disk space. So it's a good idea to work at lower simulations, lower resolutions at first, just to get an idea of how things are working out before you go to something very high res. Um, and when I speak of high res, I'm really talking about the tens of millions of particles range. So before you run one of those, make sure you do have the disk space to accommodate that much data. So I'm just going to let this write out and jump ahead to our next simulation setup. So now that we have our fluid simulation written out to disk, let's just bring it in so we can start setting up our next simulation. So let's put down a file node and just point it toward the file that we just wrote out. And while we're here, let's change this missing frame parameter to no geometry. This will just help us later on when we do some shifting around of time values. So the first thing we're going to want to do is just separate out the data that we just wrote out so that we can analyze each one individually. So I put down an add sop and connect it to the file node. And move to the Particles tab. We can turn on this Add Particles System. And you'll see that as soon as we do that, our particles appear in the viewport. And this is just a really great way of visualizing point data when there isn't already visualization data attached to it. And then if we go back to the Points tab and turn on this Delete Geometry but Keep the Points checkbox. And this basically is deleting everything but our particles. So even though we just wrote out a surface and velocity field, now we're just dumping all of that just so we can visualize just our particles. Now we're going to do the same thing, but for our fields. So let's put down a delete node and turn on delete non-selected. And we want to keep it on primitives. Then in the group, instead of putting in a group that we've created, we're just going to use the name of the fields. So if we put down @name == vel dot asterisk, that will keep all of our velocity fields. And because velocity is a vector, it actually creates 3 fields: velocity, x, y, and z. So this asterisk is just going to let us keep all 3 of those. Then I'm just going to copy and paste this delete node and move it over, and then get rid of vel and put in surface. So if we visualize that node, and scrub through the timeline, you'll see that we have this sort of fog, and that's representing our surface field, which is exactly what we want. We've isolated all 3 of these streams of data. And in fact, just to make that clear, let's actually name these nodes something useful. Isolate surface, isolate vel, keep things consistent. And on the add sop, let's put down isolate particles. Okay, so now we have these 3 pieces of information, but what are we going to do with them? So let's actually bring up the original animation I showed you and take a look at what's happening here. If you look at the whitewater, you should note a couple of things. And one is that when the whitewater lands on the surface of the water, it continues following along with it. And that's where our surface field is going to come in handy. You also see that, in general, the velocity of the whitewater is either matching or surpassing the velocity of the underlying waterfall simulation. And that's what's creating this nice splashing and keeping the fluid sort of following along the surface. So our velocity field will help us with that. Now the final thing is that the whitewater isn't sort of appearing randomly across the surface of the waterfall. It's showing up in sort of logical areas, places where the water is striking a rock or going over a fall. And we need to find a way to isolate those areas so that when we create the particles, they show up in reasonable places. So let's just start there. So let's go over to our isolate particles node and take a look at what we have. So here are our particles moving, so we need to think of how can we find the particles we need to become our new emitters. Just like previously we created an emitter piece of geometry for our waterfall, we need to create a new emitter just for the spray and splashing particles. And we're actually going to use this underlying simulation to become those new emitters. But we don't want to use all of them. We want to isolate them. So let's find a way to visualize that first. So if I put down a VOPSOP and plug it in, we can start manipulating the data that's on these particles. And if you middle mouse button, you should see a lot of point attributes. But the one we're most interested in, maybe you can't quite see that on your screen. Yeah, is this velocity attribute, the V. So if we jump inside the VOPSOP, we can start visualizing things immediately, very simply by taking the point velocity attribute, putting down a length node, and the length node essentially takes this vector and evaluates its magnitude. So in the case of velocity, it's really saying how fast is it moving. And then plug that into the point color attribute. If we jump back up to geometry level and visualize our VOPSOP, you can see that we're getting a slight change in the visualization. There's some dark here and some white here, but it's not perfectly clear what's going on. So let's just jump back inside and make some adjustments. If we put down a fit node, a fit range node, and plug it into this length parameter, what we're going to do is basically take whatever value is coming into the fit node and then remap it to this 0 to 1 range. So if we increase this source maximum, you'll see our visualization starting to change. So the dark areas are where the fluid is not moving very quickly at all, and the white areas is where it's moving quite fast. And it's just remapping this 0 to 6.9 range to 0 to 1. And that's a great way to help you start identifying what areas are useful to us. Unfortunately, velocity is probably not going to do it by itself, because as you can see, the velocity doesn't necessarily change a whole lot. It's sort of slow at the beginning and slow down here, but over the length of the waterfall, it more or less stays kind of the same. So instead, what we want to look for is not the velocity by itself, but when the velocity changes from one sort of state to another. And that'll give us places like the top of the waterfall, where the velocity was moving sort of straight along in this direction, and then ends up going downward. So we'll sort of get something in this range. The same thing is going to happen when it hits the bottom here, and suddenly goes from this sort of diagonal angle to something moving forward. So in order to test that, we're actually going to need to look backward in time. So let's put down a time shift node. Now time shift does exactly what the name implies. It allows you to sort of shift the time frame. And if you look at the frame parameter, you'll see that it's actually just set to $F. So in this case, it's just saying on frame 68, let's look at what's on frame 68. But that's not what we want. We actually want to look behind one frame. So if I just put -1 and I evaluate that, you'll see that it's actually looking at frame 67. And if I visualize it, you can see that things have changed slightly here. Now the reason we're doing that is so that we can compare the velocity of our current frame to the velocity of the frame before it, and figure out how much it's changed over that time period. So let's take the time shift node and plug it into this second input on the VOPSOP, and then dive back inside. So this setup here was helping us visualize how fast, or what the speed of the velocity was. So let's keep that around and see if we can apply it to our new system. In order to look at the information coming in through that second input, we can do that in two ways. There is an add attribute import attribute. And you'll see it has this op input index. And if we set that to 1, it will take that second input on the VOPSOP. Unfortunately, because our point values can change from frame to frame, since they're being deleted at the bottom and sort of created at the top of the waterfall, we can't necessarily count on our point numbers matching each other. So instead of using import attribute, we're going to use point cloud open. Now, point cloud open is a little bit of a complicated VOP, but we're going to use it in a fairly simple way. You can see it has this parameter for query position. If we plug that into the point position, what we're basically asking is look at our current point and then look at the incoming point cloud near that point and get some values from it. And if you look at some more of the parameters, you'll see there's a search radius, number of points to look over. But the one we're most interested in is this point cloud texture, which is asking for a file. Now we're going to sort of play a little bit of a trick and get some information in there without having to resort to loading up a file. So before we actually do that, let's take a look at what we want to get from this point cloud. Well, we want to find out the velocity of our current point, and that's this variable coming out here. But we also want to get the velocity of the points near it, so the points from this point cloud. So if we point down a point cloud filter node and attach it to this texture handle, you'll see we can filter for a certain value. In this case, it's looking for the position, which isn't what we want. We want to change that to v, which represents the velocity. So now we have the velocity of our current point and the velocity of the points from a frame ago. And we want to compare those two things. So what we're going to do is put down a subtract node. Take our velocity from our current position and subtract from that the velocity from one frame before. And this is basically creating a new vector, which is the difference between the two vectors we're putting in there. And then if we actually plug that straight into this length parameter, we're going to do basically the same thing we did before. We're going to find out the magnitude of this new vector. Or in another way of putting it, the difference between these two vectors, which is how much they've changed over that time period. So if we jump back up to our geometry level and visualize this VOPSOP, you see we're getting a result, but it kind of looks the same as it did before. And that's because we haven't set this point cloud texture properly. So if we promote this parameter and jump up to the geometry level, we can use an expression here. And the expression we want to use is op input path. Now, op input path essentially returns a path to a node. So if we put down a parentheses and then use a quotation mark, dot quotation mark, that's going to say look at the current node right now, and then a comma and a 1. And this 1 represents which input we want to look at. So we're really saying look at the node I currently am, which is this VOPSOP 1, and then look at this input, which in this case is this second input here, and then return the path of the object that's connected to it. So if we did this correctly, it should be giving us this time shift node. So if I middle mouse button on the point cloud texture parameter, it should evaluate into, oh, I'm sorry, it is a string, so we do need to put down a backtick so that it evaluates properly as a string. So if I middle mouse button now, you can see that I get this full path: object, particle fluid, time shift 1. So it's pointing to the correct thing. However, it's not going to evaluate correctly just yet. And that's because this is just giving us a string, but it's not telling the VOPSOP to actually do anything with it. So if we need to add this op command. And the op basically forces an evaluation on a node. So it sort of behaves like inputting a file. And as soon as I hit enter, you can see our visualization has changed quite a bit. Now we have a lot of sort of dark areas and just a couple of bright areas. If I dive back into the VOPSOP and go to our fit node, I'm actually going to promote this parameter. Then I'm going to jump back up to the top and start playing with this to see if I can isolate the areas that I want. But you can see now, if I scrub through these values, that I'm actually isolating some different areas. I'm getting these bright points in areas where the fluid is sort of becoming turbulent. So if I scrub through, particularly at the beginning, it's a lot clearer. These bright points are right on the front, the leading edge of our fluid. And that's because that's where it's changing the most. As we scrub through, you'll see a lot of bright white areas here when it hits the first sort of drop. And then you'll get a couple scattered throughout the fluid as it sort of churns in on itself. And then over time, you'll sort of see these bright sort of waves travel through. Now these areas are the ones that sort of make sense. It's when the fluid suddenly changes direction or becomes very turbulent. That's where we want to generate our spray. So how do we isolate that from the rest of these particles? Well, because we have this visualization information, we can actually very easily drop down a delete node, plug it into our VOPSOP, change the entity to points, and then leave it on delete selected. If we scroll down to the operation and change it to delete by expression, we can use a $CR, which is a local variable that points out the color value, and in this case the color red. And if we say $CR, or red value, is less than 0.8 and hit enter, you'll see that all the color values, in fact if I go back to our VOPSOP, basically all of these gray values, the ones that aren't close to 1 or white, get deleted. And now we're just left with the particles that are sort of changing the velocity the most. And if I scrub through here, you can see we get a nice sort of flow throughout the whole surface. But they're sort of staying more or less in the correct areas, which is in these turbulent areas here, and then there are a couple that sort of glide along with it in areas where the fluid is sort of getting churned up. This is also it shows the advantage of writing out our previous simulation to disk, because now I can make these evaluations very quickly without having to resimulate anything. So now that we have these three pieces of information, our surface, our velocity, and these new particles, which are basically going to become our emitters, let's put down a couple of nulls that will just help us point to these pieces of data from inside our simulation. Call this one out, new emitters. And then over here we'll put down another null. And a null is just an empty object that can be used as a pointer, basically. Let's call this one out, vel. And then another null for the surface. Out, surface. So with this setup, we can start building our actual simulation network for the whitewater foam sim. So let's just save our progress. So before we get started building this next simulation, let's just rearrange these nodes a little bit, since they sort of belong in the step 1 sort of section. Okay, we're going to put down a DOP network, because we're actually going to build our own simulation network for this part of the simulation. Let's just rename that Splash Sim. And then dive inside. Also, let's go back to frame 1. So this simulation, this whitewater simulation, is actually going to be a particle sim rather than a fluid sim, because we don't necessarily need the spray to behave like a body of water. We just need it to be this foaming, splashing mist almost. But we are going to drive some of the motion using our original simulation. So we do get the benefit of some of the fluid dynamics. So let's just put down a pop object. and then a pop solver. Connect these guys up. Let's just make a little more room here. So first thing we're going to want to do on the pop solver is turn off this use external pop. That's because we can actually put a pop network directly inside the solver. If you're familiar with other particle networks, a lot of these nodes should be familiar to you. If not, it should be fairly easy to follow along. So we're going to put down a source node, and this is where our particles are going to be created. If we go up to the top here on this emission type, we're going to change that to points random instead of points ordered. And then for the geometry source, we're going to use this SOP parameter here. And we can just go point directly to it. Go to our particle fluid object and select this out new emitters. And this is why we set up those nulls, so we can very quickly find the correct outputs we're looking for. So this out new emitters are the particles we isolated in the previous step. We're also going to want to adjust this birth tab. Right now it's just going to put out 100 particles on more or less every frame, but that's not what we're looking for. We actually want to very specifically create a number of particles which is equal to the number of particles in our emitter geometry. That way when they sort of jump around and show up in different places, like when it hits the landscape and creates a splash, we can always be guaranteed that particles will get birthed from there. So let's just use a very simple expression called endpoints, and that just finds the number of points in a node. And now we're just going to point it toward our particle fluid node. And then inside of that, our out new emitters node. Close off the quotations and the parentheses. And that's all we need to do. So now on every frame, it'll give us exactly the number of particles that we need. If I jump back up to our DOP level here, let's add a merge node and a gravity force node. Now the gravity is going to do exactly what you imagine it does. It's going to add gravity to these particles. The merge node I'll get to in just a second, but let's just visualize this gravity node for the moment and hit play. So you can see that, well, we're definitely getting some sort of result, and if you look closely you could tell that it does more or less match up to the shape of our landscape. So we're definitely on the right track here. Let's just go back to frame 1. One thing we're going to want to change is the life of these particles, because we definitely don't need them sitting around for too long. You imagine that's a piece of foam floating on the surface of a fluid would probably get reabsorbed into the fluid after a fairly brief amount of time, particularly if it's something turbulent like a river. And mist in the air is only going to hang around so long before it basically either evaporates or again falls down on the landscape or disappears in some manner. So let's just change the life expectancy to 1 and put the life variance at 0.25. You can play with those values and get whatever you think looks good, but that's a good place to start. Now if I hit play again, see that our particles aren't lasting forever. And we've already got a reasonable sort of representation of spray without really doing much of anything. But we can definitely make it look better. So let's go back to frame 1 and go up to object level. If we go inside of our landscape, you'll see that we're on this DOP import node. And that was for our previous simulation, so we don't want to be visualizing that anymore. Let's jump up to the polycap. Now we can use this shelf tool, static object shelf tool, to add a collision object to our new simulation. So click on the landscape node and hit static object. And then if we jump inside our new simulation, you can see it's added these couple of nodes, the same ones that it added previously. The only difference is it's added this merge node at the bottom. And that's why I added one earlier. So I can disconnect it from there. And oops, let me just unselect the nodes first. and plug that into the merge node. Then we can just blast away this guy. And now if we hit play, you can see that our particles are actually colliding with our landscape, which is really nice. We're definitely moving toward our goal here. But in reality, we don't want our particles to collide with the ground. We really want them to collide with the surface of the fluid. But this would come in handy if you had a much larger landscape where the spray could land on the rocks to the side, or bounce down the edge of a hill or something. It's useful to have this collision in here. However, if you are certain that it's only going to collide with the surface of the water again, it would definitely optimize your simulation to remove this section. But for now, we can leave it in. Let's just go back to frame 1 and dive inside our pop solver. So the next thing we're going to need to do is create a set of rules that will tell our particles what to do when they encounter the surface. And for that, we're going to use a VOP pop. We used a VOP SOP earlier to isolate our emitter particles, and this is a very similar workflow, although we are going to take a slightly different approach. So let's dive inside here. Let's make a little more room. So we need to think about what we want our particles to do. And if we break it down into very simple rules, what we're really looking for is a particle that has landed on the surface or has gone below the surface of our fluid. And since we have a surface field, which actually gives us information about what is inside and what is outside our fluid, we can use that to test our particle's position. So let's drop down a volume sample from file node. Now this node behaves very similarly to the point cloud node we used earlier. It uses a sample position, which was called query position previously. So let's plug that in. So this is actually going to take a sample of our volume at our current point position. And in the case of a surface, it's going to give us a negative value if it's inside the fluid and a positive value if it's outside the fluid. So that's a perfect place to start in order to start testing our positions. And whenever you talk about doing a test in VOPs, what you really mean is this compare node. So we can take the value that's coming out of this sample, plug it into the first input. And on the compare node, you can see the test right now is equal, and it's using this compare to float 0. So in this case, it's saying if it's equal to 0, we'll consider this a true result. And that's not what we want. What we want is less than or equal to 0. So now we're basically saying check our position in relationship to the fluid, and if it's inside the fluid, it's true. From there, we can create an if-then block. And an if-then lets us basically execute a series of commands only if this comparison value is true. And since we know we want to do something to our point position whenever it's below the surface, let's plug our point position into this first value. Unfortunately, this isn't going to give us everything we need. While it's good to know whether the point is inside or outside the surface, what we really want to know is where it should be. And in this case, it's if we go below the surface, we want to push it up towards the top. If it's outside the surface, we kind of don't really care what it's doing, so long as it's moving the way a particle would. So to find out where the surface is in relationship to our point, we can use another node called a volume gradient from file. And this one works very similar to the volume sample. We'll just take the point position and plug it into the sample position. Now a volume gradient will basically look at a field and create a vector or return a vector that points towards the surface of that field. So with these two nodes, we basically know two things. How am I inside or outside the surface, and where is the surface in relation to me? So with those two values, we can actually do something interesting. If we multiply them, and it's important to put the vector in first, but if we multiply them, we're basically going to scale this directional vector by the amount inside or outside the fluid we are. So if I'm very, very close to the surface, it will only be a very short vector, whereas if I'm really far away from it, it will be a very long vector. Now it's sort of a quirk of the volume gradient that the direction we want needs to be negated. So let's just drop that down. Okay, so right now we have a vector that points to the nearest surface, but it's still whether we are inside or outside the volume. So we definitely need to get that information inside this if-then block. But before we do that, let's put down an add node. We're going to take this vector and we're going to add it to our original point position. So that basically means we'll take wherever I currently am and move it towards the surface, which is what this block is doing. So by adding them together, our point now ends up on the closest surface to it at any given time. And that's great, except it's always going to do this. So instead, we only want to do it while it's inside the fluid. So we can take this value and plug it into this second input here on our if-then block and jump inside. So in here, you'll see we have an input and an output, and our point position and our combined value. So what we want to do in here is, if the point is inside the fluid, we want to exchange the point position's current point for this new value which we created earlier. And the way to do that is actually just to take this combined value and plug it into the output of the point position, and then go up. Now we can take the output of this if-then block and plug it directly into the point position output variable. So right now we've basically set up a system that says, find out where I am in relation to the surface, which is this section. Create a new position on the surface of the water, and if I'm inside there, make that my new position. And that's all going to work great, but we do have some issues. So first of all, we need to do something about this geometry file here. So let's just promote that parameter. And rather than leave it as a little peg here, let's expand that. And then take this file and stick it into this volume sample as well, because we're both of these are going to use the surface. If we go up to our Waterfall surface here now, we can see we have this geometry file node. And we're going to use the up command that we used previously. Except instead of using the input path expression, we're just going to directly give it the path that we want. So in this case, it's /obj /particle fluid, and you can select it from this drop down. And then out surface. And again, you can see how convenient it is to have renamed those nulls, so that if I start typing out, I get only the out values that we created earlier. Let's go to surface. Okay, now let's look at the result of what we've just done. So if I come over here to our particle sim and hit play, you can see that things are sort of definitely a little different than they were. If you look at this gap, you can see that particles that are above the fluid are allowed to sort of move freely, but nothing is really getting below the surface. And that's because if the particle is below, we immediately push it back up to the surface. And this is working pretty well, but it can cause a few oddities. If you look really closely in some areas, you'll see that the particles aren't really moving like the fluid. They're sort of just inheriting their initial velocity when they're born. So what we really want to do is add our fluid velocity into this particle velocity. So let's jump inside our Wattpop again and gather up some of that information. So previously we used this volume sample to find out where within a fluid we were. And that's because we were using the surface field. But if we use the exact same node, we can evaluate whatever data a field holds. So let's promote this parameter again. Jump up to our pop. Instead of surface, let's point this towards our velocity. So again, we just type in the path toward this out node and jump inside. Now the thing with velocity is that it's actually represented by 3 fields, not 1. So we're going to need to extract those separately. If we go to the volume sample file, you see it has this primitive number. And that relates to the number of volumes that are in this file that we're bringing in. So 0 is going to give us our x value. 1 will give us our y, and 2 will give us our z. So all we need to do is copy and paste this volume sample node. Make sure the wiring stays correct. And then make sure our primitive number lines up correctly. 0, 1, and 2. Now that we've gotten each of these pieces of information individually, we need to combine them again into a velocity vector. So we're just going to put down a float to vec node and just plug them into the corresponding input. Okay, so now we've got a new velocity which is based on the velocity coming in from our original simulation. Before we go any further, we need to make sure the point position is put into the sample position of these nodes so that we're finding the velocity in the fluid exactly where our particle happens to be. And from here we can basically do the exact same operation we did last time, which is to take our point velocity attribute and plug it into our if-then block. So that's our particle's velocity when it's outside the fluid. And then if we plug this one into our fluid velocity, we now have 2 velocities, our fluid velocity and our air velocity. So if we dive inside, we can again do the exact same process. Take our fluid velocity and use it to replace our original velocity. And then just plug our point velocity into the point velocity output. So now we've basically created everything we need. We're moving the points to the surface, and we're giving those points the original fluid's velocity. And if they're not underneath the surface, we're letting them do basically whatever it is they need to do. So if we jump back up to dot level here and play our animation, you can see we're definitely getting a nice sort of fluid animation. Some of the particles are allowed to spray up, and some of them just sort of slide along with the velocity of the fluid. In fact, if I go up to object level and go inside our particle fluid node, I can grab the original particle fluid surface node, which was created by our shelf tool way back at the beginning of this process, and just disconnect it from the original sim. And I'm just going to plug it into our file node and visualize it. And because we're working at fairly low res, we can get a surface relatively quickly from our original simulation. So if we jump up to object level now and visualize what's happening, we can see the white particles are our spray foam sim, and the actual surface is our original waterfall simulation. And you can see how the particles follow along with the velocity, but occasionally burst free and splash into the air. And that's exactly what we're looking for. And the one thing you may want to do when you get to this point is start cleaning up the particles that leave our simulation area, like these guys. There's a very simple way you can do that. First of all, we want to put down a new geometry node and call it spray geo, and then jump inside. We can get rid of this file node. If we put down an object merge change it into this object. Oh, I'm sorry, not an object merge, a DOP import. We can set the DOP network to our new spray sim and hit accept. And then change this import style from transform input geometry to fetch geometry from DOP network. And you can see immediately in the viewport we get our landscape and our new particles. Well, we don't really want the landscape, and you could delete it here, but instead let's make sure we're just grabbing the particles that we want. If we actually go up to object level and then down into our spray sim, we can see that we've created something called pop object 1, and that's what we want to pull out of the simulation. So if we go back up to our spray geo and then put pop object 1 in the object mask, we just get the particles that we want. Now the next thing we can do is put down a box. Just move it off to the side here. I'm also going to ghost other objects so we can see our landscape. Now I'm going to take this box and I'm just going to scale it to basically fit our simulation. Something like that. Let's scale it in the Y. And let it sort of fit along the bottom. Now, this is an absolutely necessary step, but it does make it a little easier to tell what's going on with our sim. So let's put down a delete node. Plug our original points into the delete node. And before that, let's put down a group geometry node. And then we're going to plug this box into the second input and visualize that. Change the entity to points. And instead of using number, we're going to use this bounding parameter. And then we'll turn on enable. And instead of bounding box, let's use bounding object, which is this object. Oops, I accidentally locked that. Now if we move through play here, you can see that points inside the box are being added to the group, and anything outside the box is being taken out of the group. So we can use that group now in our delete node. Change this to points, and under the group, just pick group 1. Now you'll see that it's actually done the opposite of what we want. It's deleted the points inside the container. So all we have to do is change this operation to delete non-selected. Now let's turn off our spray sim visualization because we don't need that anymore. Now if you look what's happening, if I go back from wireframe, we have a fairly nice clean simulation where the points are following the surface and splashing into the air. You know, it's all very low res, so obviously you can increase the resolution of this sim to get something more detailed and more interesting. But this system scales incredibly well and will give you great results no matter what resolution you use. So let's just jump back to frame 1. Let's save our progress. So just quickly to recap, we built our landscape, we created our emitter, and then we built a dynamics network that took advantage of our flip fluid solver. We also made a couple of adjustments to our emitter object using a mountain sop and a custom VOP sop. Once we had this initial geometry, we wrote it out to disk, and then we brought it in and separated it out into sort of useful chunks, including this VOP sop, which helped isolate our new emitter particles. And then from there, we built a new spray simulation and took the result of that and just cleaned it up a little bit so it was clearer what was happening. So if we just jump back to look at our original animation and hit play, you should now be able to identify exactly what's going on here. We have this underlying fluid simulation and these spray particles which are sort of resting along the surface. So I hope you were able to learn a lot and apply this to your own simulations. Thank you for your time.